Of announcements. You should pick up your graded homework, the one that you handed in on Monday, here. Exam number 2 is on Friday, 9:30 to 11. It's in 0003 LeConte, and you can bring 2 sheets of 8.5 by 11. It's comprehensive. It covers the entire course, not just the latter half. With more emphasis on the latter half. Any questions or comments? And there was a review session yesterday. And is there office hours today?
Yeah. There's office hours today, but I had to go down to Livermore, so I moved into directly after class, and then I'll have the normal office hours tomorrow.
You had the normal office hours today also?
No, not today, but I moved until right till 11 to 12.
Okay, so there's office hours by then, 11 to 12, and then regular office hours tomorrow by then. Let me just write it down. Ben, where is that? Which one?
469. Sorry.
And then regular office hours. Okay. Are there any? So today's lecture is pro bono or extra. There's no homework on it, and it's not. You're not responsible for the material. Yeah, question.
Is it no calculators tomorrow?
On Friday?
Right. I'm sorry.
You don't need a calculator at all. In the interest of people who have, there's some people who might have extremely fancy calculators and bypass this the cheat sheet things. Just let's just say no. You don't need it. Any other questions or comments? Okay. So what I thought I would do today is start talking a little bit about short-term Fourier transform, and then gradually move on to wavelets, and look at wavelets from a couple of different angles. One, from short-term Fourier transform, and two, from a different point of view, from multi-resolution analysis, which is something that the computer vision folks came up with. And then three, from subband coding point of view, which is something that the signal processing people came up with. So this wavelet stuff was formalized in some sense in late 80s, early 90s. And different communities were looking at things that related to wavelets in their own ways. As I said, the signal processing folks, the computer vision people, and also the applied mathematicians who were working on harmonic analysis. And they sort of got pulled together. So because this is a DSP course, and because we just talked about DFTs and Fourier transforms for a good part of the semester, I just thought that it's a good idea to start motivating it and approaching it from a short-term Fourier transform angle. And then I will, if time permits in today's lecture, I will also talk about it from a different angle, and that is subband coding and multi-resolution analysis. So let me begin. And this is this lecture is new, so there's no prepared notes ahead of time, so we sort of make it up as we go. But let me start by talking about Fourier analysis of signals, because I think that's the angle that we have been covering in this course more than anything else. Okay. So suppose that the goal that we have is to understand the types of frequencies and the harmonics that are present in a given signal. Okay. First of all, there is a commercial device that you can buy that does this for you. What's that called? What's a device that tells you what frequencies are present in a signal? I can hear it. Spectrum analyzers, right? It's actually a pretty hefty and expensive device. I think last time I checked into it, it's like in the tens of thousands of dollars. And the company, I think, that used to make it, or probably still does make it, is Tektronix and HP, the same guys that make oscilloscopes. But these guys make spectrum analyzers. But forgetting that for now, so real life examples. You've got some signal. It's continuous time, and somebody comes to you and say, "Hey, there's a couple of sinusoids there, or there's some frequencies that are prominent there. Go compute for me. Go figure out using all these DFTs and FFTs and all these tools that we just learned over this last semester. Tell me what frequencies are present in that signal." Okay, so we're dealing with Fourier analysis of signals, And we want to use all the tools that we have. In particular, we want to use DFT, because remember, that's the only thing that computes Fourier transform. It's the only computational box that we have. So you're given some sort of an analog continuous time signal. And that signal we call S sub C of t. This is continuous time. And you're interested, the signal could be extremely wide band and have large bandwidth, but you're interested only in its harmonics in some particular region. So what do you do with this thing? You start with that. You go through some sort of an anti-aliasing low-pass filter, just so that you limit its frequencies a little bit, and I call that H sub A of omega. And then you do a C to D, continuous to discrete time conversion, and this is matched to the bandwidth of this filter. You get X of n, some discrete time signal. Then what? Then what you have to do is the signal is of an infinite extent in some sense. You have to multiply it by some sort of a window function. So you multiply it by a window, W of n, so that you look at a finite piece of it. Because DFT takes what? A finite length input sequence, endpoint, for example, and generates an input-output sequence. It doesn't deal with infinite length sequences. So there has to be some sort of an operation where even though the duration of the signal is from minus infinity to infinity, and by the way, no signal in the universe is from that length, but you want to look at a piece of it. So that brings up another interesting notion, and that is the concept of frequency. In this course, we've been thinking and talking about frequencies without worrying about when those frequencies occurred in a signal. Okay? And that is sort of a motivation for introducing short-term Fourier transform, which will come in 10 more minutes. Okay? But I'll emphasize that when we get there. But for now, let's say you multiply this by some sort of a window, and now it's a finite length signal, V of n, and you just pass it through the DFT box, and out comes V of k. Okay, so this is now finite length. And this is the window. Okay? And so let's just understand what goes on in this block diagram in terms of the spectrum of the various signals that we're dealing with, just so that we know what's happening. So you start with some spectrum here, and I'll first draw it roughly by hand, and then I'll show nice pictures from Oppenheimer and Schaefer because they can draw it so much better than I can. But here's our the S sub C of omega, the Fourier transform of this guy. Let's say it looks something like that. It goes all the way to plus infinity. And then after you low-pass filter it, you can sort of eyeball it. Let's say we low-pass filtered it, let's say H sub AA of omega looked like this. Or then after you low-pass filter the signal here, which I call X sub C of t, is going to have some spectrum that looks like this. Let's say this thing we already know because the semester is over. You already know this brick filter is impossible to realize in real life, so it's some sort of a thing like that. So after this comes out, then it's going to look something like that. At this point, you discretize it, and what does the discretization do? When you sample a continuous time signal, what happens to spectrum? And what's the spectrum? How is the spectrum of this related to that? We all know that relationship. It's this thing replicated with period 2 pi, depending upon, let's say we just critically sample it. In other words, we sample it just at the right frequency so that we don't oversample, we don't undersample. And what comes out of here is X of omega. Oh, I didn't draw it right. And then, okay, so this goes from minus pi to pi because I critically sampled it, and it repeats itself. And now what happens? I multiply, and this is the exact kind of analysis I'm hoping an analysis I mean plotting and sketching that I'm hoping this course has drilled into your head and you can do very easily. But what happens when you multiply by this window? Well, depending upon what the Fourier transform of the window is, you get different answers here. So, so that's actually another interesting point. Let's come back here. Yeah, great. So, suppose that I have a Fourier transform of W of n. I call it W of omega, and suppose that thing looks something like this. Okay, and perhaps it has some ripples here, etc. The magnitude of it looks something like that. And finally, so that's this guy. And so now, because this got multiplied by x of n, this gets convolved with this thing. And what comes out here is this thing convolved with that. So it could be, the two peaks could be there. And then finally, it goes from minus pi to plus pi, and that's v of omega. Right? That's the Fourier transform here. And now finally I take samples of this thing. Because I take the DFT of this, I'm taking equally spaced samples, and boom. So these are the numbers that I end up getting. Okay? So a lot of things happened in this block, in this chain of events. And a lot of things could have gone wrong if I didn't. There's a lot of parameters. That's what I'm trying to say. There's a lot of parameters, and depending upon how you pick those parameters, a lot of things could have gone wrong. So staring at this picture, and can you zoom out just a tiny, tiny bit? Great. So staring at this picture here, what are the parameters and what could have gone wrong? Suppose our goal was, we knew there were sort of two peaks there, and we wanted to know where those two peaks are. What are the things that could have gone wrong if we didn't choose the parameters? So what are the parameters here? First is the anti-aliasing filter. If I picked the anti-aliasing filter wrong and got rid of this, then I would have never seen those peaks in the final answer, right? Here, the final answer is giving me samples of this, right? So for one thing, I should have an idea of what the highest frequency in my signal is and what the bandwidth of the anti-aliasing filter is. Okay, that's one issue. What else could have happened? Well, because I know what, if I have matched this anti-aliasing filter to the bandwidth of this, and if I furthermore matched my sampling frequency t to the bandwidth of this, then I can avoid having aliasing. So aliasing is something else that could have gone wrong. But let's say we did that correctly, and we got that correct. And we've already dealt with that. What else could have gone wrong? You're multiplying by this window function here, right? And what is the duration of that window? If the duration of window was too short, then the Fourier transform of this thing would have been too fat, right? That's the old windowing stuff that we talked about earlier. So if the window was too short, this thing would have been too fat. And if this thing was way too fat, when I convolve this with this double hump spectrum, I just get a blah like that, right? And would I be able to detect that there's a peak here and there's a peak here? No. Those would have been completely gone, right? So ideally, I should pick this window function large enough so that so that this thing is narrow enough so that I don't smear my x of omega too much, right? And the last thing I have to do is choose the length of the DFT. If I didn't pick, even if I picked this window long, and so that the Fourier transform was narrow, so that the frequency v of omega was faithful representation of this. If I sample my DFT at too few points, which actually in this case I'm sampling it to match the length of the window, so it's more or less the same thing. So if the window was short, not only would I get a blah, but then I'm sampling this blah at coarse samples, I'll definitely miss what's going on, right? So I'm matching the length of the DFT to the window. But but if you do all of these things right, you get a reasonable answer. And let's look at some of these professionally done spectrums by Oppenheim. So here is, if you zoom in all the way, thank you. So here's the Fourier transform of the original signal. There's a peak at omega naught. That's the thing we want to determine. We want to know which omega naught it is, for example, that's happening. That's the anti-aliasing filter. That's the spectrum of a continuous time signal after it comes out of the anti-aliasing filter. This is after we digitize it. It just gets replicated, and I'm assuming that we're sampling it so that there's no aliasing, and so this is what we get. This spectrum of the discrete time signal. This is the spectrum of the window, and this convolved with that gives you this. And notice that these peaks here are sharper, and even though this window was good enough, because it was an infinite duration and because this wasn't exactly a delta function, there is some blurring of these peaks happening. And then I sample these at 2 pi over n. This is what endpoint DFT does, and boom. These are at the end of the day, when somebody comes to you and says, hey, what frequencies are present in that signal? You have n numbers to give them. 0, 1, 2, all the way to 10 comes down. These are the n answers that the spectrum gives you. In the real life, there's no DTF. You can't compute DTFT. You can compute X of Z. All you have as a tool for computation is the DFT, and that's the answer. Okay. So now let's move on to a slightly different example. Any questions on this? So I think it was pretty straightforward. It ties in a lot of the stuff we did in the course. So now let's move on to another example. Okay, and let's understand this effect of windowing that we just talked about just a little bit more. So let's consider our continuous time signal is to be sum of two sinusoids. Okay, so I have S sub C of t is A naught times cosine omega naught t plus theta naught. That's just some arbitrary phase. Plus A1 cosine omega 1t plus theta 1. And this signal goes on from minus infinity to plus infinity. It's a long, long time. And suppose that I sample this and there's no aliasing and no quantization. It's a sample, no aliasing, no quantization. Nothing goes bad here. And what I get is a discrete time signal x of n, which is A naught cosine omega naught n plus theta naught plus A1 cosine omega 1 n plus theta 1. Okay, and so in this case, omega naught is just omega naught t, and little omega 1 is capital omega 1 t. That's just what happens when you do sampling. Okay, so start with that, then you get that. And now suppose that I window this x of n with a window function, which we call w of n. And what comes out is this. V of n, this new signal that we just talked about, is A naught w of n cosine omega naught n plus theta naught plus A1 w of n cosine omega 1 n plus theta 1. Okay? So I can rewrite that, because I want to do easy Fourier analysis on it, as sum of exponentials, because then it allows me to take its Fourier transform really easily. So I can just say this is A naught over 2 of w of n, and this cosine just becomes e to the j plus this plus e to the minus j of that. So it'll be e to the j theta naught e to the j omega naught n plus A naught over 2 w of n e to the minus j theta naught e to the minus j omega naught n. Sum of these two things makes up this. Plus, do the same thing here. It's A1 over 2 w of n e to the j theta 1 e to the j omega 1 n plus A1 over 2 W of n e to the minus j theta 1 e to the minus j omega 1 n. So these two things make up that. So having done that, what is the Fourier transform of this? How can I write the Fourier transform, v of omega of that thing? Well, I'm going to go to a new sheet because I don't want to run out of space, but given that v of n is this, what's v of omega? Well, the Fourier transform of this is just sort of a delta function. So it's a naught over 2 e to the j theta naught. That's all the constant. And what's the Fourier transform of this e to the j omega n? Well, it's the Fourier transform of the window, but just shifted by omega naught. That's the shift property of the Fourier transform. Again, you've got to know these things, at the top of your head. So it's W, which is the capital W, which is the Fourier transform of this, of omega minus omega naught. Again, plus a naught over 2 e to the minus j theta naught. What's the Fourier transform of W n times this? Again, shifted version of that. W of omega plus omega naught plus a1 over 2 e to the j theta 1, W of omega minus omega 1 this time, plus a1 over 2 e to the j theta 1, W of omega plus omega 1. Good, we're done with that. Now what I'm going to do is I'm going to try to show you some plots that I keep the window size fixed. I keep it at 64. And I'm going to show you some plots of V as I change omega naught and omega 1, or alternatively in our continuous time signal, this omega naught and capital omega 1. So the plan is, let's just keep a naught equals 1, a1 equals 0.75. Let's make the sampling rate t to be about, or rather 1 over t to be about 10 kilohertz. And let's make theta naught equals theta 1 equals 0. We don't want to complicate things. And let's say the length of the window, first of all, we pick a rectangular window. Of course, you can choose any other one. But let's say we pick it to be 64. Okay? And then what happens to V of omega, or magnitude of V of omega? Okay? For different values of omega. So then the plan of action is I'm going to make the distance between omega 1 minus omega naught, which is the distance between these two frequencies in my original signal, smaller, progressively smaller. I'm going to make it progressively smaller, and I'm going to show you what happens. So the experiment is this. Make the distance between these things smaller and look at magnitude of V of omega. Okay? So here we go. First of all, if you have a 64, zoom in, yeah. First of all, if you have a 64-point window, this is the magnitude of the Fourier transform of the window. Not a big deal. This is what happens when omega naught, is 2 pi over 6, and omega 1 is 2 pi over 3. Okay? I mean, this little omega is 2 pi over 3, big omega. And little omega 1 is 2 pi over 3, little omega naught is 2 pi over 6. As far as capital omega naught and capital omega 1 go, they're given by these quantities, which if you multiply by 10 kilohertz, you get rid of the 10 to the 4, which is 2 pi over 6 and 2 pi over 3, right? Everything is in check. Everybody agrees? The relationship between little omegas and big omegas is just through t, right? So that's so is that good or bad? It's fantastic. Does that give us a good notion of what frequencies there are present in the signal? That window, did that window screw things up? No, not too badly. Initially we had 2 peaks at these 2 things, and then now after we multiply by the window and take this is now discrete time Fourier transform, not just DFT, but it's at least apparent in the DTFT. If you lose it in DTFT, you have no chance ever to catch it in DFT, right? DFT is just samples of DTFT. Now this is what happens if, as those frequencies get to be closer, little omega naught becomes 2 pi over 14, and little omega 1 is 4 pi over 15. So they got a little bit closer. We can still resolve those two frequencies. This is what happens when they're really close. Omega naught is 2 pi over 14. Omega 1 is 2 pi over 12. So you can see there's the two things are leaking. And why are they leaking? It's the window function, right? It's the window function that's getting convolved with the Fourier transform of the original signal. And here's what happens if the peaks get, the frequencies present in the signal are really close to each other, 2 pi over 14 and 2 pi over 25. Then there's just one blah. So this technique of multiplying by the window was ineffective, in a sense, in terms of identifying where the two peaks were. And it has nothing to do with DFT, and we didn't take it fast enough, to, high enough samples of DFT. It just has to do with the window function. Okay? So the ability to detect the frequency of the signal using the window technique sort of goes away. So that gets us thinking about an entirely different notion, and that's the notion of short-term Fourier transform. Okay? So, and the short-term Fourier transform doesn't exactly solve this problem, but in considering it actually addresses a slightly different problem, and it addresses the problem of what frequency occurred at what time type thing. But short-term Fourier transform is also plagued with the same window problem that we just talked about here. And one of the motivations, or one of the exciting things about wavelets, is that it doesn't have this window problem that we're talking about here. And hopefully by the end of the lecture, I will get to explain why and how and everything else. So let me just change gears a little bit and talk about the short-term Fourier transform. So what does short-term Fourier transform do, or what is the definition of it? I'm going to stick to continuous time short-term Fourier transform. So the short-term Fourier transform of some signal as a function of tau and f. So short-term Fourier transform now is not just as a function of frequency, but it's telling you at what time what frequency occurred in a particular signal. I'm going to write down the definition of it, and then I'll motivate why it makes sense and what it does and all those other things. So the definition is the integral of x of t g complex conjugate of t minus tau e to the minus j 2 pi ft dt. Okay? So, and this goes from minus infinity to plus infinity. So this is the short time Fourier transform of x of t. So you have a signal here. And the motivation, again, is that suppose I'm not just interested in knowing what frequency is in the signal. I want to know what frequency occurred at what time. So I have a signal that has this low frequency stuff here, and then 5 minutes later it has these high frequencies, and then 2 minutes later it has these medium frequencies again. And I don't want to just do Fourier analysis on this end-to-end, because then I have to have a huge window function, and that window function blurs each one of these and all kinds of other issues. Rather, I want to know at what time each of these frequencies occurred. And what's some examples of applications for which that's important? Anybody?
Speech recognition.
Absolutely, in speech. In speech, what happens is that there's a thing called spectrograph, which I'll show you. Actually, why don't I show it to you right now as a motivation? When you talk, you don't want to be taking Fourier transform from minus infinity to plus infinity in order to figure out what phonemes and what things are present in your speech. rather, you want to look at it as a function of time. You say, at this time, this person said this. At this time, this person said that. And so an example of spectrograph, here we go, is shown here. Okay? Can you zoom in, please? Or focus, rather, sorry. Is this... Oh, I want to be able to read these words. Okay, good enough. So this is what you have up here is a wideband spectrograph, and on the vertical axis you have frequency, and on the horizontal axis you have time. So this person is saying these words, and right here is the waveform of what you're talking. It says 2 plus 7 is less than 10. So this is this is frequency, this is time. So what we've done is we've taken the speech waveform, we've multiplied by window, and then at the window centered around the particular time, and then we take the Fourier transform of it, and then we plot that Fourier transform along this axis here. And then we shift the window ever so slightly, center it around a different time, you get a new signal, take the Fourier transform of that, and then stack that up here. Shift the window some more, take the Fourier transform, and you just stack these things up. And so this is the, if you will, the time varying Fourier transform of this, or short-term Fourier transform of this signal. Okay? It's a two-dimensional picture. It's no longer like a frequency plot that you're used to, you've been using in 120 and 123. It has a frequency and it has a notion of time. Okay? And so, coming back here, so what's exactly happening is I have this function g. Let's say I pick some sort of a window function that I like, whatever that it is, and I think of it as a string attached to the center of this thing. This is centered around time tau. And I change this tau, and I drag it along here, and at each position, multiply this by that, get a one-dimensional signal, and I take its Fourier transform and plot it. Then move this a little bit to the right, here, multiply this by this, take a Fourier transform. Some more, multiply this by this, take Fourier transform. More. And then I can come up with a plot as a function of tau and f. Right? So for each value of tau, I multiply this by that, and then I'm taking its Fourier transform. That's what this equation is all about. And I get an answer, and I stack up that answer like that. There's a thing sticking out of the plane here, out of my paper. It's a one-dimensional function, and then for each tau, I get a different one-dimensional function, right? You can easily imagine how this short-term Fourier transform can be discretized. You discretize the tau, it slides over different at discrete times, and when you multiply by window, you get finite number of samples. You sample that and take the DFT of that, so you can discretize along f as well. Okay, so that gives us the short-term Fourier transform, which is a two-dimensional transform of a given signal. Okay. What is the problem with short-term Fourier transform?
It's short
Mm-hmm.
term. Is that a problem?
The fact that it's short-term enables you to tell you what happens locally, not globally. Right? If I was just going to take a Fourier transform of this whole gigantic thing, I get a whole lot of things all smeared together. But here, I can get the frequency, and I can tell you what happens here, then tell you what happens here, then tell you what happens here. So that, in some sense, that's good. But what's the problem with it? What parameter does it have that I didn't tell you yet, or I didn't talk about it too much? this window G. And the problem is that the size of this window is problematic. Why? Well, let's do a little thought experiment. If the size of the window is big, right? What's going to happen? Let's say if the size of the window is big like this, then I have failed to tell you at what time this frequency occurred, right? I lose temporal resolution. I can't tell you at what time my frequencies occurred, right? So if I'm doing the speech analysis, all those words get blurred out, and you get garbage out of it. So ideally, what you like to do is to what? Is to have to avoid that problem, you want to make your window small. And what could go wrong if I have my window too small? Exactly. If you make the window small, you lose frequency resolution. What do I mean by that? Well, I mean like this. If suppose I have a window of this size, and for me to be able to detect that there's a frequency of f0, I have to have at least a couple of cycles of that frequency within my window. Let me exaggerate now here. If my time signal at a particular time is doing this, and then at a different time is doing this, if I pick my window too small, like this big, it's good for detecting the frequency here because it incorporates few cycles of this, but it's not good for detecting what frequency occurred here because the cycles of these guys are long. One cycle goes from here to here, and that's much longer than that. For this, if I multiply this by that and then take the Fourier transform, I'm not going to be able to detect what this frequency is. Okay? So the fundamental problem with short-term Fourier transform, and by the way, short-term Fourier transform was used extensively in the signal processing community before '89 or all those times. But the fundamental problem is how to figure out the duration of this window G. So problem is duration of G. If G is too large, then I lose temporal resolution. That means I can't tell you at what time a particular frequency occurred. If G, I mean extent of G, that's what I mean. If the extent of G is too small, then I lose spectral resolution or frequency resolution. Because I want to have at least a couple of cycles, or the more cycles of it I have, the better I can figure out what frequency there was in it. So in general, if I have a window function g of t and its corresponding frequency, Fourier continuous time Fourier transform g of f, and this is my window function, then I can define this quantity delta f rather delta f squared as f squared magnitude of g of f squared df over the g of f squared df. This is sort of tells you what the spectral resolution of this window is, roughly. There's many other measures one can come up with, but this thing tells you that two sinusoids can be discriminated if they're more than delta f apart. Okay, so for a given window, g of t, which corresponds to g of f, two sinusoids are discriminated. That means you don't get this blurring that you saw earlier. Okay, if they are more than delta f apart. Okay? So remember, if the extent of G was too small, we lose spectral frequency, right? So this relates. This is a sort of a more formal mathematical tightening of this statement here. And you can also tighten this other statement here, which has to do with temporal resolution. You can say that if I define this quantity delta t squared as integral of t squared g of t magnitude squared dt over g of t squared dt, then this is the temporal resolution. Then two pulses can be discriminated or if they're more than delta t apart. So for a given g of t, two pulses can be discriminated if there are more than delta t apart. So that's the more formal statement of this thing that we had here about the losing temporal resolution. So it seems like we're between a rock and a hard place. Why? Well, because there's a relationship between g of f and g of t. You cannot have delta f and for a given function g, for a given window g, you cannot have delta f and delta t to be arbitrarily small. Ideally, you want delta f to be small. You want to be able to resolve two sinusoids that their frequencies are really close to each other. Ideally, you also want to be able to detect two sinusoids that are very close to each other in time. That's the ideal world. So ideally, you want delta f to be very small and you want delta t to be very small. But that ain't going to happen because what? What's the principle that we all know about that prevents us from doing that? It's called the uncertainty principle, which says that you cannot have functions whose Fourier transform and whose g of t are arbitrarily small. Okay, alternatively, their delta f times delta t cannot be too small. So there's a thing called uncertainty principle that goes like this. It says that the time bandwidth product, which is delta t times delta f, is always larger than 1 over 4 pi. Okay? So we can't have delta f and delta t to be arbitrarily small. And what's the consequence of this thing is that once you pick a window function, your temporal resolution and your spectral resolution is fixed for the entire time frequency plane. Okay? So once you pick a given g of t, the temporal and the spectral resolution is fixed for the entire time frequency plane. And what do I mean by time frequency plane? I mean this tau versus f plane that we just talked about. Right? So the delta f delta t is the same as here, as it is here, as it is here. It's all over the same. Okay? And so once you nail that in your application, you can have high temporal resolution but low spectral resolution. You can have, or you can have high spectral resolution but low temporal resolution. Or you can make those things medium, but you can't do better than that. And this is in contrast with what, well, let me first draw one more plot here. And what this is telling you, what essentially this short-term Fourier transform is doing for you, it is, if I go back to the old Fourier transform one-dimensional plots that we have, x of f, what short-term Fourier transform is doing, you can think about it, is that it has a constant bandwidth filters that divides the frequency axis on. So it tells you what's going on with center frequency of f0, then f1, then f2. You can think of this short-term Fourier transform in two different ways. Or, I mean, where is the plot here? I can think of, when I take the short-term Fourier transform of a signal, two different ways. Either I can look at a particular time t0 and look at this one-dimensional plot and see what it's doing and tell you what the frequency content of the signal at that time is, or at this time is. Or what I'm trying to say is I can also look at it for a fixed function f0 or a fixed function for fixed frequency f0 and tell you that at that frequency as a function of time what signal I'm getting. Right? So if there's a two-dimensional function sticking out of the board, taking the cake analogy and cutting analogy, I can either cut my knife like that, or I can cut my knife like that. If I cut here, I get a function, I get a one-dimensional function going up and down here, and that's this. The same thing as this. Or I can cut it like this, and then get a function like that. So this, right? Because this is a two-dimensional function. So if I do it this way, it tells me at a given time what frequencies are present, which is the spectrum, the notion that you're familiar with. If I cut it like this, it's telling you at a particular frequency what the function looks like as a function of time. And what is that? That's like filtering. That's like having filtered the signal at that frequency, having a bandpass signal, having a bandpass filter that passed the signal components, the signal frequencies around that center frequency, right? And this is what I'm plotting here. I'm saying, look, if I look at these red lines here, it's as if I have f0, f1, f2, center around f2, and then center around f3. That's essentially what short-term Fourier transform is doing. It's just telling me, and the way it's doing it is because I have a function g that's constant here, then these are of constant bandwidth. Okay. So what does continuous time wavelet analysis do that gets around that? So wavelets were in some ways introduced to get around this inherent problem of temporal / spectral resolution limitation. What does the continuous time wavelet do? What its intention is to change delta t and delta f in the time frequency plane. So depending on where you are, you want to change delta f and delta t so that at higher frequencies you want your window function to be of shorter duration, and at lower frequencies you want your window function to be of larger extent, right? So the idea behind wavelet is to adapt with that function, that g guide, the duration of it, depending upon the frequency. Okay, so the basic idea is to vary delta t and delta f in the time, in the tau / f plane, to get around to get around short time Fourier transform resolution problems. Okay. So in particular, what we want to do is we want to make delta f over f to be constant, or we want delta f to be proportional to f. This is exactly what I was saying. You want, depending upon what the frequency is, you want the frequency resolution to be dependent on the absolute frequency you're looking at, right? Or alternatively, you want to make delta t to be proportional to f. So when you go to higher frequency regions, you want to have effectively windows that are bigger. And the way you do that, let me just define now what the continuous, so having to plot this picture again from scratch, the way you would do it, can you go up to the, so essentially what I'm saying is, as a function of frequency, what you want to be doing is dividing your band, your filter bands. Remember, this picture was a result of this thing, right? These two guys. So you want this picture to change a little bit, in a sense that you want to have a narrower band filter here on F0, slightly wider, centered around 2F0, and then yet much larger, twice as large, in fact, around around 4F0, and something even much larger around 8F0. So you want the bandwidth of these virtual bandpass filters that, remember, these are sort of equivalent to bandpass filters, right? You want the bandwidth of these bandpass filters to be proportional to the frequency they're centered at. So when they're centered around 8F0, you want them to have big bandwidth. When they're centered around 4F0, smaller, 2F0, smaller, and F0, smaller. That's what I mean by saying that I want delta F over F to be roughly a constant, or I want delta F to be proportional to F, or delta T to be proportional to F. We want these delta F stuff to be a function of, you want all the parameters of your filter to vary as a function of the frequency that you're looking at. So in this time frequency plane, when you will end up having effectively different window sizes as you move along the frequency axis. Okay? And so what would be a way of achieving that? Here's a definition of continuous time wavelet transform. I wrote Fourier transform so much I can't even write wavelets. So here's the wavelet analysis and synthesis equations that allows you to achieve that. You say continuous wavelet transform of this function x as a function of tau, and now I'm not going to use frequency anymore. I'm going to use the notion of scale a, and it becomes clear in just a second, is the integral of x of t times, there's 1 over square root of a here just to take care of normalization factor, times h of t minus tau over a dt. Actually complex conjugate. Okay? So forget about the fact that I'm calling f a, but it doesn't matter. And this goes from minus infinity to plus infinity. But here's the thing I want you to notice. You start with one function. I've called it h instead of g, but what the hell? It's the same thing. It's the same window function that we had before. But when I'm analyzing, how does this function look like? Well, let's compare it to what we had before. Let me just show you what I had before. I had g of t minus, I have the integral from minus infinity to plus infinity, the x of t, something complex conjugate. I call it h here, I call it g here. And then I have t minus tau here, I have t minus tau here. But it's the over a that changes things. I'm starting with h of t, and at different frequencies, I scale it by different amounts, right? So h of t over a, when a is equal to 1, could look like this. When a is equal to 1. What does h of t over a when a is equal to 2 is going to look like? It's the same as h of t over 2. If h of t looks like this as a function of time, how does h of t over 2 look like? Anybody? It's the same thing, but compressed, exactly. So if, for example, at frequency, at that time 10, it took on this value here, now it takes that same value at time 5. So it's going to be this. Wow, I draw this so many times. If it looked like this before, it's not going to look more compressed. How about h of t over 4? It's going to look even more compressed. Okay? So this is everybody following? What the? Oh, the other way. Sorry. Let's go to a new page. So if h of t looks like this, h of t over 2, whatever value it took on at time 10, now it takes it at time 20. It's going to look like this. Okay? And h of t over 4 is going to be even bigger. Okay? So does that make sense? Yeah. Essentially, the window or that you're using, it's changing its scale, it's changing its frequency as you look at different frequencies. Think of let's not even call it scale yet, that comes later, but think of this as frequency. And when I'm looking at a particular frequency, I'm changing the width of this window, just like I'm supposed to be. And does that make sense? Yeah. As A becomes larger, as I'm looking at higher... A is the opposite of frequency. As I'm looking at lower frequencies, I want to have my window to have larger duration. So frequency and scale are inversely related to each other. So this is called scale. And in fact, A is inversely proportional to F. Okay? So as A goes up, then the duration of my coating code window, i.e. h of t over A, goes up, and therefore I can do better frequency analysis. So that's the thing that I was talking about. We have made the duration of window to be proportional, to adapt to the frequency that we're looking at. Okay? So you could then, and what's the synthesis filter? What's the inverse of this guy? Well, the inverse of that guy is just this. It's x of t equal to some constant, and then double integral of continuous wavelet transform as a function of tau and A, of the signal A, and then 1 over square root of A h of t minus tau over A dA d tau for all a's larger than 0. Okay? So this is a continuous time wavelet transform, and this is the discrete, I'm sorry, this is the inverse of it. This is the analysis part, then this is the synthesis part. And what I want you to walk away with is that the continuous time wavelet transform over one-dimensional waveform is a two-dimensional thing. It's a function of tau and A, it's a function of tau and A. Okay? And you might say, okay, we looked at spectrograms a second ago for a speech signal. That was the short-term Fourier transform of a speech signal. We can also now talk about the equivalent of this. We can look at this function for different signals and see how that looks like. That's called scalogram. So this thing is called a scalogram, as opposed to spectrogram. So spectrogram was for short-term Fourier transform. This is for continuous wavelet transform. So how do these things look like? Well, just before I show it to you for some actual signals, let me just show it to you for some simple signals like a delta or a pulse or some sinusoids, just to develop intuition as to how this function here looks like. Okay? So let's zoom into here. If we can. Okay. So on the top, what I'm showing you here and here is the continuous wavelet transform and short-term Fourier transform of a direct pulse. That means a pulse that is of duration delta t, and it goes up and then down. So it's sort of a delta function type thing. And it's centered around time t naught. Right? So you have a thing that goes at time t naught, and sorry, this is a delta function, and depending upon what window you chose, there's a delta t. What you get in the short-term Fourier transform domain, this is time, and this axis is frequency. The frequency axis is going that way. You get all frequencies in a delta function, but there's a smearing in time. Why? Because I'm multiplying by a window of finite duration, right? That's the delta t. That's the smearing because of the short-term Fourier transform's inherent temporal resolution. And for wavelet transform, you hit it that this is scale going down. Versus scale is the opposite of scale A is inversely proportional to frequency, and then it propagates something like that. These are all sort of hand-drawn type examples. Same thing for when you have sinusoids. So suppose I have 3 sinusoids of frequencies f0, 2f0, and 4f0. So this is short-term Fourier transform. This is time axis, and this is going that way up is the frequency axis. And so there's centered around f0, centered around 2f0, and centered around 4f0. And the width of these things is delta f, because that's the inherent spectral resolution of short-term Fourier transform. Even though the sinusoid was smack at f0, by the time I do short-term Fourier analysis and that multiplied by the window and all that junk, I introduce smearing of delta f. That's what that delta f was all about. How about continuous wavelet transform, where here, going down in this axis is f, and going up is, going down is scale A, and going up is f. In fact, A is equal to inversely proportional to f. And so this is what I mean by saying that the spectral resolution is frequency dependent and the temporal resolution is frequency dependent. I still have some blah at f0, 2f0, and 4f0s, but the uncertainty or in f0 is smaller than 2f0, sinusoid at 2f0, and this is smaller than that, right? So that's sort of the picture. I think this guy has drawn it the reverse. It should have been the other way around. Yeah. I'm not sure. What's not clear is what this paper assumes where the shaded regions are. I mean, I assume this is delta f, but yeah. So the thing to remember is scale and frequencies are inverses of each other. Okay. Now coming back here, here's some pretty pictures of the spectrograms and scalograms of different sort of signals, right? And unfortunately, this is a black and white printout of a paper that initially was in color. So I got it off Melville, and my printer is color itself, but the Melville holdings or scannings of these articles are all in black and white. But anyway, to give you an idea, on the left-hand side, you have magnitude of short-term Fourier transform, and here you have short-term Fourier transform. Here you have magnitude of the wavelet transform, and then phase of the wavelet transform. This is of 2 direct pulses. And here is some other pretty pictures of magnitude of short-term Fourier transform wavelets, etc., etc. But having said all of these things, I want to just end the lecture by talking about discrete wavelet transform, because that's what, again, at the end of the day, gets to be computed. Okay? So the idea behind, so continuous time wavelet transform. I have time, I'm going to plot, instead of scale, which is A, I'm going to plot log of A. Okay? And so the question is, so I have a signal x of t, and I come up with this two-dimensional, two-dimensional continuous time wavelet transform. How do I discretize it? Well, you sample. It turns out that you can sample this plane, and if you do the sampling properly and do all kinds of things properly, then you can get a discrete time wavelet transform. So we make the sampling in the time domain to be uniform, but in the scale domain, in order to have this property here, we make it uniform as a function of log of A, not A itself. So in other words, I'm going to sample in the scale domain. In the log of A, I sample it uniformly. And then here, at small values of log of A, I sample very high and temporally. And as I go here, I subsample this. And then I subsample this even further. I subsample this even further. And as I go down the scale, I subsample this plane even more. So the fact that my window function changes its, if you will, bandwidth as I move along the frequency or the scale allows me to change the sampling of this plane as I move down the scale axis. Right? Because if I'm multiplying by if I'm multiplying by a window that its bandwidth changes, there's no need to. I don't have to sample that as high as I would have otherwise. Right? So let me just write down. We're out of time. Let me just write down what the expression for discrete time wavelet transform is. Where what you do is you end up sampling this the h function that you had, so you come up with h sub j comma k of t as it's a naught to the power of minus j over 2, h of a naught to the power of minus j, t minus kt, and then this results in wavelet coefficients then that are given by cjk, which is x of t, h, j, comma, k, complex conjugate, which is this thing, of t dt. Okay? And then you can further impose conditions on this guy h. You can make these guys orthogonal, so to get orthogonal wavelet basis, then you make these guys to be orthogonal with each other, which means hjk of t times h complex conjugate j comma k of t dt is equal to 1 if j equals to j prime and k is equal to k prime, and it's 0 otherwise. And if you do that, then you can write down x of t as summation over j comma k of cjk's times h of j comma k comma t. So you have one function h, and you scale it like it's shown here to get a series of functions hjk's, and these guys are just the same function but scaled with this process of more or less the same way as we did this thing, okay, but just in the discretized domain. And it turns out you might ask questions: can we find functions that can be orthogonal? Can you find functions that when you shift them like that, at different scales they can be orthonormal? The answer is yes. And that's what the wavelet pioneers in the early 90s came up with. Durbochet and Malard, they came up with a particular set of functions that did this. And by the way, this function h has got to be a bandpass type of signal. That means that the integral of it, dt, has to be 0. It means that it has to have no dc components to it. But anyway, so there are functions that are orthonormal, and then they result in a wavelet analysis that looks like this. Unfortunately, I didn't get a chance to talk about the discrete time case. I'm sort of relating it to subband coding, but I hope that this gave you a sort of a feeling of where wavelets come from and what they're good for and what differentiates them from other things. Okay, I'll see you all on Friday then.